Okay, so this will have to deal with the audio quality might be a bit lower today. We're going to get started. So within today's class, I'm going to be building on some of the videos that I asked you to view, and also on to the past few lectures, lectures which have varied in their coverage from system dynamics analysis components to also their coverage of the basics of agent-based modeling. So I'm hoping within a single example to help reinforce some of those items and give you some practical skills that you'll be able to use on problem sets and on exams. Okay, so I'm going to pose a challenge to you here, and this challenge is going to consist of a set of several sub-challenges that we're going to work on. And these challenges will require a combination, on the one hand, of pen and paper solutions. So get your paper ready, or get ready in a Word document to write some things down. On the flip side, they will also require any logic. We're going to be doing a bunch of any logic runs in successively more articulated models. So, what I'd like to pose to you is a very simple sort of conceptual model that we're going to build. It is going to posit having a population where people in the population get sick with flu approximately one time per year on average. The average time between flu occurrences is about a year. And when they're sick with the flu, they have it for about a year, and then they recover from it. Okay? And the idea is we're going to assume that having caught the flu and having recovered from it, they'll stay recovered and immune to the flu for about 6 months' time. So here's a question. How would I characterize that sort of system in a system dynamics model? We're going to put aside the issue of transmission, which we did cover in system dynamics, but for the simplicity of purpose and allowing us to get through more material, I'm going to be pretending essentially like the occurrence of flu is just one of those random events. People are traveling all around the world not catching it from each other. They're catching it just from places outside of the model that you folks don't have to worry about. Or you could consider this, instead of flu, being a foodborne illness, where you just pick it up directly from the environment, from eating something bad rather than from another person. So how would I characterize that in a system dynamics model? Anyone want to put forward a suggestion? How could I characterize a situation like this? What would I need? So people can get sick. A given person who's susceptible to illness will get sick on about once every year or so. A person stays sick for about a year, and they tend to recover and stay immune for about 6 months, and then they can get sick again. How would I do that? How would I characterize that in a system dynamics model? Anyone?
Stock where the six.
Good. Okay. So I like hearing about stocks and flows, and we're going to be comparing this to how we do it in an agent-based model. So we have a stock. How many stocks might we have to characterize this? 3. 3 stocks. Good. Okay. And we've seen them before, right? Okay. So susceptible people who are infected. Okay, so a guy ate some bad food or got infected with the flu, and people are recovered, right? Okay, seen this before, right? And now we're going to have people who need to travel in flows. Where would the flows be? Based on my description, where would the flows go? seen this sort of thing before. Just want to go over it in our heads. Where would the flows be? Okay, S to I like it. John? Yeah. I to R, and R to S. Good. Okay. So, I said a susceptible person will tend to get infected on average in about a year's time. How would I capture that? Give me a sort of natural way to capture that we've seen many times before. So it has to do with this flow, right? So what would I put in that flow? S squared plus R?
S times 1 over 365.
Okay, right. Okay, and just to sort of make this easy, I'm going to create a little thing here. Maybe I'll make it, maybe just to sort of stir up memory, so I'll have it be called alpha, and this will be alpha times S, okay? So you have a 10% chance per year of getting sick, and there are 1,000 people at risk, about 0.1 times 1,000 or 100 of them per year get sick, okay? What is the value of alpha going to be here? I heard it earlier.
1 over 365.
1 over 365. Why? So if this is in time and days, this is exactly right. Where does 365 come from? Days in a year, right? And this is therefore 1 over the average time until someone would get sick, right? Okay, good. How about for this guy here? Recover on average in about a week's time. How would I capture that?
I over 7.
Good, good, okay. So we'll have another constant here. I'll call it delta. We'll make delta, just to give a bit of variety here, to emphasize this will be 1 over 365 days, right? This will be about 7 days, yeah? That's not a 0.7, that's a 7. Okay, good. Okay, excellent. And the formula here would be what in this case? I over delta, that's right. Alternatively, we could have called it gamma and made it 1 over delta and multiplied, made it I times gamma, right? Okay, good. And then we're going to have this last one. It's going to have a mean time before recovery of 6 months. So, anyone? How do we do that?
1 over 1 week.
Yeah, something like 1 over 180. Okay. It won't beat you particular, so that's great. So R over 180, right? R over tau. Yeah. Okay, good. Okay. Great. So I want you to tell me how to solve this system for its equilibrium values. In other words, what's the value at which it's in balance? Nothing's changing. We're going to solve for that. So what do I do? What do I need to do what do I need to do first to do this? What should I write down? Okay, say this again. I heard a Greek chorus. Unfortunately, my knowledge of Greek was limited, so I couldn't make out everything at once. So, what was that? What should I write down here?
S dot.
Okay, S dot, good. Equals, anyone want to fill in S dot?
0.
I'm sorry?
0.
S dot, okay, so we're going to be solving for S dot equals 0. That's right. But what is the formula for S dot in general? We're going to be solving for a very particular case where it equals 0. But what's the formula for it in terms of these things in the model? In terms of, if we consider the rate of change of S, how quickly it's going up or down, based on the current state of the model.
R over T minus alpha times S.
Good. R over T or tau minus alpha times S, right? This is the inflow. This is the, and 10 people are coming in and 5 are leaving per day. Then you've got a net rate of increase of 10 minus 5, or 5 people per day. Make sense? If an equal number are coming in as are going out per day, you're going to have a net rate of change of 0. It's going to be in balance, right? You got water coming in as fast as it's going out. Okay, good. Okay, so this should be quick work. Remind me your name again, Arlen, right? Thank you. Okay, I dot here. Fill them in. Conservation of people on this. What has to be here? Alpha S. Okay.
Subtract I over delta.
I over delta. Good. Okay, excellent. And R dot?
I over delta.
R dot is I over delta. Yeah?
Minus R over tau.
Okay. R over tau. Okay, good. Okay. So we are going to solve for the equilibrium situation with this model. Okay, so how do we do that? I heard it earlier from Arlen, right? We would set what? We would solve for the case where what is the case? Where S dot equals 0. What else equals 0? I dot. Everything has to be in balance. The system has to be in an equilibrium. It's like homeostasis, right? Our body's in sort of state of balance. Okay, great. So we'll do that. And so what that implies is that R over tau minus alpha S equals 0, right? And secondly, that alpha S minus I over tau, excuse me, I over delta, no tau's here, equals 0, yeah? And then, right, the final thing, I over delta minus R over tau, writing one where I should be writing the other, equals 0. Okay, now, I'd argue I can try to solve that, but I'm doing too much work. Why? Because we know, given S and I, we know what R is. The whole total population has to total up to some value that's known. Call it N, right? So, rather than solving 3 equations, we could simplify our life, solve 2, as long as we here replace this by N minus S minus I. People comfortable with that? Right? This is the number of people in R. This is just R, but we can simplify our life, not have to deal with the other vagaries of solving for a 3rd equation, but just solving for 2 equations where we substitute N minus S minus I for R. Okay, good. Are people okay with this? Okay, so let's solve it. How would I solve it? Well, I'm going to get formulas for these things for S in terms of I. So, simplest thing that looks like is this guy down here, right? I get S in terms of I or I in terms of S, either one. Multiply this bottom guy by, so I'll put him up here, right? Should be able to do this comfortably. This bottom guy would be alpha times delta times S minus I equals 0. And what does that imply about the value of I? So I just multiplied both sides of this by delta, right? So this guy became alpha delta S minus delta times I over delta, which is just I, equals 0 times delta, or 0. So I got this. You comfortable with that? Yeah? So what does that tell us about the value of I? I equals alpha delta S. Great. Okay. That's a start. Hey, that tells us something. In equilibrium, the value of I is going to be alpha times delta times the value of S. Okay, that's great. But part of the point, it allows us to solve this more messy equation up top here. Yeah? Let's get this delta up where it belongs. There we go. Okay. Okay, so let's solve the top equation now. Boom, 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 boom. Okay, so we have n minus s minus I, n minus s minus, and we could just substitute for I, right? Alpha delta s over tau minus alpha times s equals 0, right? Okay, now we got these things all in terms of s's. Okay, great. Great. So let's multiply by tau, shall we not? Let's multiply by tau here. Great. Okay. So we're going to multiply by tau. I'll do this longhand for those copying it down to avoid erasing things. This thing minus alpha tau s equals 0. Great. Grouping the s's, what do we got? We can move all the s's over to the right-hand side here. We have n on the left equals, we got 1s plus, from this guy here, we get an alpha delta s from this guy, and we have an alpha tau s from that guy equals s, and s in short equals n divided by this guy here, okay? Okay. Now, let's see if that makes sense. First of all, is it dimensionally consistent? Okay. So here we have people on the right-hand side. S is in people. N is some count of people. And what's the denominator here? What's the denominator here? Well, alpha has units, well, it's got to be 1 over days, right? 1 over days to multiply by s and have something people per day. So alpha has units 1 over day. That's great. And what are the units of tau? Of delta. What's the unit of delta? Days. It's in days because we divide by it and have people per day, right? And what's the unit of tau? It's days also. The unit of tau is days. Okay, great. So what we have in the denominator is 1, which is it's not clear what unit it has to be. Alpha times tau, 1 over day times days gives something, units cancel, it's dimensionless. And then alpha times tau here, alpha times tau also cancels. So we have something that's dimensionless in the denominator. So we have people divided by something that's dimensionless, something that doesn't depend on dimension. So it's indeed dimensionally consistent. So that looks good. Let's think about, does it make sense? Okay, suppose tau gets really, really, really big. What fraction of people will end up in the susceptible state, do you think? This is like the fraction of all people. So the thing, we could think of this as n times 1 over this thing, n times 1 over this thing. So 1 over this whole thing, 1 over 1 plus alpha times delta plus alpha times tau. That whole thing is sort of the fraction of people that end up susceptible. So if tau gets really, really large, what is the fraction that end up susceptible? Anyone? It goes to 0. That's right. By the way, I'll write that. Thanks. I saw Ansgar rising in the back to try to view this. It's Ansgar, I'm going to put it up on this screen here. It's n times, and it's times some fraction. What's the fraction? 1 over, and the denominator is 1 plus alpha delta plus alpha tau. Alpha tau. This is what I derived. This is what I derived through this. Okay, this is kind of the fraction that ends up susceptible. So if tau gets really, really large, no one is basically going to be susceptible. People basically won't recover back to a susceptible state. They won't lose immunity, so they'll stay recovered, and therefore almost very few people will be susceptible. Okay, no one will be susceptible eventually. The tau gets big enough. Okay. Secondly, you'll notice this is with some fixed rate per year. Okay, suppose now by contrast delta gets really large. So people just back up in the infective state. What fraction of the people end up susceptible then? Suppose delta gets super large. What fraction end up susceptible? People are backing up here. No one's going on from here, right? So what fraction are going to be susceptible in the long term? This is going to be super big. So 1 over a super big thing is close to 0, right? Great. If alpha is super big, what fraction will end up susceptible? 0, because as soon as people come in here, they're going to zip out, right? Does that make sense? Think about that. They come back in here, and if alpha is incredibly big, like you have, if you have, an average time of 0.2 nanoseconds before you get sick with the next foodborne illness, you're going to be, very few people are going to be susceptible. They're all going to be laying at home in bed and in the bathroom and in various places. Okay? You got that? So think about the limiting behavior. Think about whether this makes sense. And it does. It does make sense. By contrast, if you think about, well, if delta, for example, were super fast, going to 0, then the rate limiting step will be associated with this loss of immunity. So this would basically just bear a weight of 1 over 1 plus alpha tau. By contrast, if losing immunity was super fast, if tau went to 0, then we'd have something like this, where the rate limiting step is recovery from infection. Okay, so this is great. We have a formula for S, and we have a formula for I as well. Give me the formula for I based on the below. Anyone? What's I? Okay. Alpha, so we know from over here, it's alpha times delta times S, right? And thanks to Alan, the good TA, I have all these different markers. Take a look at that. You rescued them. You remember that? Yeah, the rescue mission. Okay. So this is where we got that. Thank Alan for that. Okay. So in short, this one is n over, and I'm going to multiply alpha delta over 1 plus alpha delta plus alpha tau. Okay, that's great. And I can go solve for r, but time is a ticking, and I want to get you doing some modeling. Okay? So we just solved formulas for the number of people in each stock, and the fraction, in fact, who are in each stock in equilibrium. What fraction of people are in the I stock or in the S stock? Okay? And you could reason about this as, delta becomes really big. If delta becomes really big, what fraction are in I? Anyone? If delta becomes big, what gets big in this formula? This quotient. What gets big? This term in the denominator gets really big, doesn't it? Starts to dwarf. Whatever these guys are added to it, this guy starts to become really the biggest. And in the numerator, it becomes really big also. So this whole thing approaches what? 1. Approaches 1. Basically, if delta becomes super long, super big, basically everyone backs up in I. No one's in R, no one's in S. Basically everyone's in I, right? Does that make sense? Intuitively? You grok it? Grok or not? Okay, Grok. Okay. At least I heard one utterance. Yes?
If you say that it's going towards 1/2 because there's alpha in 2/3.
Okay, that's a great question, John. I should have said as delta becomes really, really large. And I think I started my utterance with that, but then I somehow wandered into the unfortunate territory of talking about how alpha grew. So it's actually, if delta grows really big, everyone backs up an I. Suppose alpha becomes super big. Can anyone characterize what? What if alpha becomes super big? What fraction of people are insusceptible? We talked about it earlier. If alpha is super big, what fraction of people are insusceptible? Close to zero, right? Because if alpha is super big, they're just rushing up. That was the 10 nanosecond between foodborne illnesses, right? Which is a most unpleasant prospect. Okay, suppose, however, alpha is very, very large. Pursuant to John's question here, what fraction of people end up in I? Suppose alpha gets super high. Sorry?
All the population.
Yeah, so, okay. Is it all the population?
Almost all.
What happens as alpha becomes super high, the numerator divided by the numerator plus the numerator divided by the denominator approaches what? Alpha gets really big, so it's alpha delta over, you can basically ignore the 1. The 1 is peanuts. It's tiny. It's infinitesimal compared to these big, giant alpha deltas at alpha taus, right? Those are like the Mongo terms, right? And so basically it now becomes something like alpha delta over alpha delta plus alpha tau, right? And essentially you can divide through by the alpha. Alpha is really big after all. It's not zero. Divide both, so it approaches what? If alpha goes to infinity, what is I approach?
1/2.
Is it 1/2? Is it always a half? Isn't it? It's delta over delta plus tau, right? Okay, that's what it is. That's the fraction. Why? Because it's alpha. It's essentially very, very close to alpha delta over alpha delta plus alpha tau. You divide the alphas on both denominator and numerator, and you get alpha over alpha plus, delta over delta plus tau. Does that make sense? I want to get you thinking about the intuition for these things. It's not just arbitrary formulas. And I want you, if you go into your exam, to reason this through and think, does this make sense? It'll help you spot errors, right? So as alpha approaches infinity, I goes to that. As delta goes to infinity, I goes to what? As delta goes to infinity, we said it earlier. Anyone? It goes to, in other words, the total number of people in I goes to n. It's fraction 1. And as tau goes to infinity, what does I go to? Yeah, 0. Because basically this denominator is super big, and the numerator can't even keep up. It's peanuts compared to the denominator. So it goes to some small thing over some super big and increasingly humongous thing. Okay? So it goes to 0. Does that make sense? Okay. Okay, so we solved this, and it's a thing, well, okay, at least to your instructor, it's a thing of beauty. I won't ask, don't worry, beautiful or not. Okay, so, let's now build an agent-based model. What do you think? Okay? We're going to go create this in an agent-based model. So, what do I need to do in my agent-based model to capture a similar circumstance? What construct will I use? Will I use stocks and flows in this model?
No.
No. Stocks and flows, after all, capture the number of people in different categories. What will I use? How will that model be organized? It'll be organized according not to stocks, not divided up according to the state of people or their characteristics, but divided up into individuals. And each of those individuals will use what construct to capture their possible states. It will use a state chart. State chart. We've seen it before, and we shall see it again. Okay, so ladies and gentlemen, let us go and retract this untoward mixer. Okay, come on, I want to, there, go away. Okay, so I want to call up AnyLogic, and I would like to create a new model, and this model will be called equilibrium comparison ABM. Okay, so here's my AnyLogic. I'll say new model. It'll be called equilibrium comparison ABM, and I'm going to put in CMPT 394 T12015. Okay, so ladies and gentlemen, here we have this model, and I'd like to get rid of, I'd like to get rid of these distracting models. So I'm going to do File, Close, Others. Boom. Okay, so here's our model. We're going to, I could have you, and I pondered having you create this as a stock and flow model, but we've done that sort of thing before. Ladies and gentlemen, I'd like to create this as an agent-based model. So what do I need to do? Suppose these are persons in each of those stocks. What would I do? I would new agent type. Mark my words. I could right click here and do new. Alternatively, I could do file, new agent type that way, right? In fact, there's additional ways too. I'm going to call this a person, and I'm going to, I think I'll just say next here, and let's choose a picture for the person. Okay, let's make it a 2D picture. I don't want to get too fancy into 3D stuff yet. Okay, 2D person, and there's their silhouette. Okay, and I know some of you are eyeing these things down here. I have a feeling we'll get some fighter jets in the room. Okay. So Alan stands ready. Okay, so we got our person and we got an image on the person. If you didn't add that image, you could always go at it down here from pictures, okay? To suit your fancy. Great. So here's person. Terrific. Suppose, ladies and gentlemen, we want to create a population of these people. How would we do it? So we have these people, they're dignified by an appearance. How would we add a population? Okay, good. So open main, be very clear about what you've got open at a given time. We want to put this into main, that's where the population lives, and we want to drag in person here, okay? And we want, as we drag in, we'll rename it population, or you could do so through the properties. And what else do I have to do to render this into a population? Change it to be a population. And we're going to make it an initial number of agents of 1,000, pursuant to my comments. Okay? Great. 1,000 people. Okay. Ladies and gentlemen, mark my words. Build early, build often. So go up here and build your model. Make sure it's a happy camper. Okay? Okay, next. I'd like you to run it. What should we see if we run it? Yeah, we'll see them atop each other. How will we know, in fact, about whether there's 1,000 of them? Well, we can use this navigation menu. We'll see 0 to .999, right? That's an indication there's 1,000 people in this population. The problem is, or we could click on this and we'll see that there are 1,000 agents, okay? I'm trying to show you some life skills that you'll be using. Okay, so let's spread them out over space. Let's do this in a general way. I taught you last time, rehearsal, how would I spread them out over space?
The initial location.
Yep, go to, excellent, Wade. So go to the population and say, we want to place this agent for initial location in the specified point, and we'll do a draw from a uniform distribution, uniform from 0 to 500. That's a continuous uniform distribution, okay? And that will allow those people to be distributed. I happen to know 500 is the width of the space, but if you'd like to be careful, if you'd like to be robust, which I always welcome, you could put this dot space width here, and you could put for the Y location 0 to this dot space height, and that will be more robust. Why? Why would that be more robust? That's right. So if we changed, remember, so much of software engineering, and I would include here building models as software artifacts, is about protecting yourself against gratuitous risk of change. Protecting yourself just in case the project or the product has to evolve quickly in some direction. You have the requisite flexibility. It's easy to do. Bugs won't be unnecessarily introduced. So putting this in place gives us the flexibility of changing, as Bo alluded to, the size of the space with minimal hassle. So here we go. If you have that, do people see that? If not, Alan stands or sits ready. Alan? Okay, Alanian help is needed in Sector 3. Okay, who else needs help? Okay, Sectors 1 and 2 are quiet. Okay, great. So we're a good start. But now, ladies and gentlemen, we have these people already distinguished by population, and we could give them extra characteristics. Let's go, however, lend them some behavior, shall we not? Let us lend them behavior similar to that. Okay? Okay, ladies and gentlemen, how would I lend them behavior? I heard it earlier. In fact, it beckons. Even in the agent palette, we see the basic mechanisms we can use. What mechanisms are they? What constructs lie before us that can enliven these agents with behavior?
State charts?
State charts, indeed. So let's draw the state chart. Let's drag a state chart entry point, and let's call it health state chart, okay? So we've dragged that in. And now we will draw how many states into this agent? Sorry?
3.
Indeed. 3. Okay, let's call the first state susceptible, second state infected, because they're not really infective, truly. They're not spreading it, infected. And the third state we'll call recovered, right? Okay, recovered, great. What transitions need to adorn the state chart? What transitions? Are we done with the state chart? Mark my words, ladies and gentlemen. State charts. I spoke about agent-based models having a collection of characteristics, and I listed them, in fact, for you. Parameters that encode assumptions. States. We saw parameters last time, did we not? What did we lend the agents last time? We lent them an income. That was a parameter, right? And we can do it this time, and we'll go that direction. States are another thing. But beyond that, we sometimes just distinguish actions, things that change their state. There's the states themselves that they could be in, but then there's actions by which those states are modified. Getting infected, recovering. And then there are rules for those actions, rules. Okay? There's also an element of time. What's the time model? Is it continuous or discrete? And there's an environment in which they interact in general. This model is going to be focusing on these upper components, and I would posit before you, I would argue, I would submit that these state charts capture 3 of these elements, list of these 4 elements listed here: parameter, states, actions, rules. Which 3 do they capture? A state chart. They certainly capture what? States. What else do they capture? Actions, right? Change between those states, yeah? And then, in fact, the rules under which those changes take place. So, ladies and gentlemen, building on that knowledge, what do I need to add to the state chart to make it whole? Transitions. Good. Excellent. Okay, so let's add a transition. This transition will be called infection, okay? We could think of this as a case of foodborne illness, infection. Someone gets sick with E. coli or with well, hopefully not botulism. It would require a more serious transition to death. Okay, infected to recovery, we're going to recovered, we're going to call it recovery, okay? Now, you notice I'm being a little bit, I'm not really paying attention much right now to the particular of the transition logic. That has to do, after all, with the rules. I'm just drawing out the actions right now that change the state. So let's give these things names. It's not clear right now. I called them this, and I'd like to show the name so you could see it there. And then this one, we should go show the name, shall we not? Okay, now I see a most untoward thing here. You notice it's saying seconds. I forgot to do something very important. What was it? Set the time unit. Where do I do that? I do it for the whole model. Go back and click to the model as a whole and set its time units to be days. Okay? Days. The unit of the model is days. Okay. The infection transition, we want to show the name. The recovery transition, we want to show the name. And what other transition do we still have to add?
Waning of immunity.
Waning immunity. Excellent, excellent, excellent. Okay. So let's go add that. Make sure when you connect these, mark my words, make sure when you connect these that they turn green on both sides. Not because they're sick with foodborne illness, but because they're indicating that it's connected, in fact. Okay? Okay. So this transition we call waning immunity. Okay, great. Okay, so we've encoded now the actions, but we need to specify the rules by which they take place. And you notice when we added this latest transition, its default unit was days, because that was the default unit of the model. Okay, great. So, ladies and gentlemen, if we want to capture the same type of logic over there that we captured in yonder model, in that system dynamics model, how would we do it? What sort of transition would adorn this transition, or what sort of rule would adorn the transition between susceptible and infected? Would it be a timeout after a fixed amount of time? Would it be based on arrival of the agent on some destination? Would it be a condition? It would be a rate. And it will be a certain amount per day. Be sure to change that per day. And what would that be per day? What's the chance per day? It's actually exactly analogous, ladies and gentlemen, to here. What's the probability per day of transitioning? 1 over 365. Now, ladies and gentlemen, we're not in Kansas anymore, so we have to be careful how we describe this. I'm going to say 1 over 365. What do you think I'm ignoring here? Anyone? Computer scientists speak as in one voice. Units. What will this evaluate to? To what? Okay, but what will the numeric value of this be in Java? 0. Why? Because 365 goes 0 times into 1 as an integer. So we could change this to 1.0 divided by 365, and that will solve all problems, for example, right? Okay, good. Okay, now recovery. What sort of transition will adorn this? It's a rate as well. It'll be a rate per day of what? Okay, good. 7, okay, excellent. And now, for this final transition, what sort of transition? Rate. Everything in a system dynamics model, in a traditional system dynamics model, is going to be a rate transition, a certain chance per unit time. It's memoryless. No matter how long you've been in the infective state, you have that same kick of the can over the next day to recover. That's what a rate transition is associated with, and this will be 1.0 divided by 180. Okay? Good. Okay, ladies and gentlemen, what if I were to run this model? What would I expect to see?
Nobody getting infected. Everyone just remains susceptible.
Okay, why would that be? You think? Well, we don't see this. Let's go down and look at each person in the population. Oh, look at that. They're ripping through these things, are they not? Right now, there's just a fixed chance. So what you said earlier would make sense if there was nobody, if people got sick from each other, but here it's just a fixed chance. So people are, in fact, progressing among these transitions. It's just hard to see visually. So ladies and gentlemen, let's lend them an appearance, shall we not? What do you think? Okay, I don't hear protest. In fact, I see a measure of willingness. Okay, so let's go to person, let's go to presentation, and let's expand this presentation area and find person. And there's a thing in there called shape body. Okay? Okay. And you'll see that we could set the colors here. And you'll notice the fill color here, for example, can be set to be dynamically set. See that? Watch, even as I change it. I could set it to be drawn from a value. But how am I going to keep track of this value? How could I make them different colors? Anyone who watched the video, perhaps? What would I need? What could I do?
Use a variable.
Use a variable. Good. So let's add a variable, and this will be of type color, spelled according to the dictates of the American Imperium. The capital C, right? Because it's a class, right? It's an instance of this class is what we're going to store here. Its initial value will be black, okay? And then, how are we going to change its color? At what points will its color change? Anyone? Where are some places that I could tell something to happen, where I can perform work here? Anyone?
In the transition.
Indeed, I could do it in the transition. Sometimes, however, a given state has multiple transitions into it, and it's actually sometimes more convenient to actually put it in a state. So let's go to the state here, and we can put in place an entry action for this state. States have actions associated. So much of building models in any logic is about associating actions with particular events to make things happen. So when someone enters the susceptible state, I'm going to set color to equal green. Okay? Color equals green for the entry action to susceptible. For the entry action to infective, I'm going to make them red. and the entry action to recover, I'm going to make it gray. Okay? Gray. Okay? Okay, great. So I'm just assigning to this, oh, we should have called the variable color, sorry, I fell asleep at the switch. COLOR. If people wish, they could put a U in it. And susceptible, we'll assign it to be green, infected to red, gray to recovered. Okay, great. Now, will this model magically be colored now? What do we still have to do? Change the shape body such that it declaratively depends on that variable. So we're going back in person to presentation, person, and shape body. Who needs Alan's help here? Okay, great. Go to shape body. Anyone else? Okay. Shape body, go to fill color. Change it from this sort of static equals thing, which you could use to set it statically, to this thing that indicates a loop, and set it to be what? What do we type here? Color. Good. Okay. Ladies and gentlemen, we finished a logical chunk of work that coheres, work that goes together. And now it is time to build. So we build. With this a software project, when you finish a logical chunk of work, typically bigger than this, you not only build for a small chunk of work like this, but a somewhat logical chunk, you might do some testing, you might get someone to look it over, you might document it, you might check it in. Okay? So we just built this. Okay, ladies and gentlemen, I'd like to run this now, run this model. Okay? Let's go see what happens when this model. What do we expect to see? Okay? Good. What do we see? Speak on, use. What do we see? Okay? So who needs help here? Okay? Okay, sector 1, sector 3. Okay. So, Aiden, do you think you might be able to help this gentleman at all? As you enjoy your measure of previous experience? Okay, do we see this sort of thing? This is a checkpoint. Okay? This is a chance to check something. Okay? Folks, do we see this? No? Okay. Okay. So who needs help? Professorial help is on its way. Okay. Okay. So what happens when you? Okay. So what you need to do here is in color, you need to make this capital C color. Okay. Because it's a class. Who needs professorial help? Okay. Good. Yeah. Oh. Okay. Okay. So what you do is like there's no guy. He's a nice guy. Okay. So go delete this guy. Okay. And then okay. Now go over to palette and now go to this guy down here and drag this guy. I forgot about that. And now you can follow my instructions here. Here's a person, and you go to shape body, and you have it in shape body. In appearance, you have it for person. Okay? So, okay, I'm sorry. Oh, okay. Okay. This is in name. Oh, this has to be in person. Yeah. So copy all this chunk of stuff, put it into person. Yeah. Okay. Thank you. Okay, who else needs help? Do people see this? Okay, if you see this, I'd like to do a calculation now. So I'm going to introduce to you one more piece of the AnyLogic toolbox here, because you're going to be wanting these things for your problem sets and projects. Ladies and gentlemen, I would like to go to main. But first I would like to ask you, what fraction of the population do you think is infected at a given time there? Yes? Question. Okay, question? Yeah?
No, with some kind of rocket.
Okay. So do you think you might be able to help this gentleman in the back of Sector 2? Okay, so quadrant 2A. So any questions on what we just did? It's a broad issue. What fraction of that population of 1,000 do you think are going to be infected at any one time? Roughly. Well, it should be very similar, I would argue, to this. So let's go figure out how we can calculate that. So first we have to calculate how many people are infected at a given time. Okay? So ladies and gentlemen, let's go to the population here. Okay? We're going to go to the population, and we are going to go to the statistics area of the population. Yes, Alan?
Actually, some people are wondering, can you just go through how you get your colors one more time?
Sure.
It's a common question.
Happy to do that. Thank you, Alan. I appreciate people bringing this to Alan's attention. So I went quick, and I was fleet of foot. Okay? So here I added color to this model in essentially 3 broad steps. Okay? Step 1. I added a variable called color with a lowercase c. Okay? Now, for this variable is of type color, capital C, because this is the Java class. Thank you. And I made it initially black. Okay, that was step 1. Okay, step 2, I went and I inserted entry actions into each of these states to set that color to corresponding particular colors, to set that color variable to corresponding particular colors. Green is the color for susceptible. For infected, I set the color to be red, and for recovered, I set the color to be gray. Okay? That was step 2.
And it's important how you spell gray.
Yes, indeed. It's not Earl Grey, it's Gray. Yeah, I always get it confused. I always do autocomplete. Remember, autocomplete is your friend. I suspect most people in the room learned that a couple years ago. Control space, right? Option space on the Macs. Okay, so you can. I always forget whether it's E or what A. So, okay. So gray. So that was step 2. First step: add a color. Set it to be color, to be type capital C color, be initially black. Step 2, go and set the entry actions for each of these states to assign it to nice colors, particular colors, assign the variable. Step 3, and this was the one that had the most texture. Go over here within person, go to presentation, open up person. There's a thing called shape body. And in shape body, I scrolled down to appearance, and I saw there was a thing called fill color, and I changed it from being this equal to being this thing that looked like a loop. And that allowed me to type in COLOR. Are people okay with that? Those 3 steps. And that will be a recurring thing you see on other problem sets, and it's something that's a very frequent sort of bit of work. And so here we go. It should be flashing like that. Do you see your model doing similar things? Okay. So now, anyone have an additional question before I proceed? Okay? So, let us, ladies and gentlemen, put in place the mechanisms to allow us to compute a fraction of people that are infected at any one time. So first we're going to go into population. Okay, so watch this. Go into population, and I'd like you to scroll to the area that says statistics. Do you see that? Okay, now I'd like you to put in a statistic called count infective. Okay? And this is going to be, again, any logic does a lot in a declarative way, and in statistics are no exception. So we're going to declare what this statistic counts up, and it's going to take care of implementing it. So this is a statistic of type count infective. It's going to be type count, and the condition here is going to be, we're going to be going through each person in the population asking, are you infective, are you infective, are you infective? And the way we refer to each person is actually indicated by this little light bulb. It says use item, colon, the embedded object. So we actually refer to each person in term as item. And we ask item dot is, and we will ask is, so okay, yeah, I thought it was is in state. Is, no, dot in state, that's what it is, in state, and we will say in state, and we will give it the state name person dot infective, okay, person dot infected, sorry. So this is what I'm putting there. I will put it on a big screen so everyone can see it, okay? So here we go, boom, there we are. That's what I put under the condition. So how does this work? It's going through each person in the population in turn, calling them item. And it's saying, okay, for that person, are they in the state, the infected state, as considered from the perspective of a person? After all, we could have an infected mosquito and be mosquito.infected, or an infected deer and be deer.infected. Okay, this is, for those for computer science, this is a static variable of the class. Hence, we could just say person.infected. Notice person is capital P. Okay? Are people comfortable with that? Do you have that in place? Okay, shall we build early, build often? Build the model. Make sure it's a happy camper. Alan stands ready. Okay? Thanks, Alan. Okay. Is this okay? Did it build early? Build often? Did it build? Okay. Let us now run it. Run. Okay? Now you should be able to go up to this population here, and you should be able to click this, and you'll notice that count infective here is gyrating around. What's going on? Okay, you can ask them. So what do you think's going on here? Well, there's stochastics, aren't there? Okay. Okay, ladies and gentlemen, let's now do a plot of this. How do I do a plot in any logic? We've done this before. How would I add a plot? Anyone?
Analysis.
Good. Let's go to the palette, the analysis area. Okay, and we'll add a time plot. Okay. Yeah. Here we go. Time plot. And what will we plot? We will plot data item. So this will be plot stocks. Sure. Stocks. Okay. And let's add a data item. And mark my words. This will be called infected. So count infected, let's say. And the key thing here, ladies and gentlemen, for the value, let's put in population dot count infective. Oh, you know what? I called it infective. I should have called it count infected. I'm sorry. Time is short, and so I'm not going to go correct it right now, but I stand corrected. It's actually, they're not infective. They're not spreading the bug. They're infected. Okay. Do you see what I did there? Who defined this? Who defined this? From whence did that come?
Is it auto-generated?
Yes, it was auto-generated. We defined the statistic, and it auto-generates this function. Okay? Okay. So now let's go down and let's just make this more tractable. We'll have it update every 1 day. This is down in the data update area, and I'd like to define it so that it shows for up to sure we could say display up to 500 latest samples in the time window of 500. Okay, that's great. Okay, so having done that, I'd like you to run it. Okay, remember that this total population is of size 1,000. Where is this? I put mine above here. I put it up there. I will slow it down a bit. Now you'll notice a couple things, and it's instructive to sort of reflect on them. First of all, you will notice that this is varying from time to time. What's going on? Why is it going up and down like that? Well, there's stochastics. There's uncertainty. These rate transition, a given time, a person's either in susceptible or infected or recovered state, and they transition suddenly, according to this probability. But at a given time, they're in exactly 1. And so the number of people who are infected at a given time will oscillate somewhat. It's the vagaries of someone getting infected and someone recovering, etc. So we actually see that it's somewhat variable. However, it does have a sort of equilibrium value. It has a value that it's sort of roughly equal to on average. And what do you think that value is? Roughly speaking, what do you think it is? Just looking at this. What do you think it is? 15. Yeah, somewhere around 15 or so. Yeah. Okay, now let's go and see if this jives. After all, this model is the analog to this model here, is it not? We just kind of translated this model into an agent-based way, right? All of these guys here, which have a certain probability per day of going on this transition, were just translated to similar rate transitions. If we ran the system dynamics model, would it do this? Would it do this jagged thing? No, it would be smooth, right? It would be smooth and right in equilibrium. Because it's not quantized, it's not broken up into particular individuals. Okay, ladies and gentlemen, so now let's calculate what fraction, according to our theory from the system dynamics model, what fraction of people should have been recovered, or how many of them? First of all, what is n for this model? I asked you to set it to 1,000, right? Okay. So within our ABM model, we should have I equal to roughly 1,000 times, and I'd like you to read off here. So alpha here is 1 over 365, right? Alpha is 1 over 365, good. And what is delta here? 7. Delta is 7, good. Over 1 plus, and again it's I'll just abbreviate this, 7 over 365 plus alpha times delta. So alpha being 1 over 365 and delta being what? 180? Yeah? Okay. So does anyone want to do that calculation? Anyone want to? You could pull up your handy Excel, or you can do it on a calculator or what have you. I could do it on the tools here. Here's KCalc, right? And the numerator would be 7 divided by 365, right? 0.19, and I could divide this by 1 plus 0.019 or so on, plus, and it's going to be plus roughly 0.5, right? Yeah, okay. And she gets something like this, about 12% or so. Is that right? What did you get? I did a rough calculation there. What did you get? Anyone? Who did the calculation directly in Excel or some other thing? What value would that be? What did you get? What's the fraction? What is this fraction? Sorry? I'm sorry? 15%. About 15%? Something like that? Okay. So what we see here is pretty similar match in terms of overall proportions, but there's a lot of variability. A lot of variability here. Let's play this out, though, just a little bit more. First of all, let's stop this model, and let's put it in a different form here. Let's do this. Ladies and gentlemen, I would like you to go to person here, and I would like to actually set this infection to no longer be a rate with an average time of 365 days. I would like it to be an exact time of 365 days. How would I do that? With a what sort of transition? Anyone? With a what transition? Timeout transition. So let's set it to be a timeout of 365, not seconds, but days. Okay? Days. Boom. Great. Okay? Now I'd like to set the recovery time to be a exact timeout of 7 days. 7 days. And we're keeping the average the same. It's just we're setting them all to be the same. Right? And on this one, I'd like to set the timeout to be what? For this waning immunity. To keep it the same average, what will the timeout be? 180 days. Okay, what do you think we expect to see? If we run this model, build early, build often, what do you expect to see? Anyone? Should we see the same thing? We're keeping the average the same. All we're doing is we're changing it to be a timeout. What should we see?
Everybody's changing all at once.
Okay, so here we go. We're running this model. Why isn't everyone changing? Why aren't they changing? Why is no one turning red?
365 days.
Okay, it hasn't gone 365. Okay, watch this. Let's speed it up. What do you think's going to happen? Boom. Okay. Okay, what's going on here? Boom. What's going on, ladies and gentlemen? Now they're all synchronized because they're all on timeouts. Are they not? We're getting a pulsing of the population there. Same average, but now everyone's coordinated. Okay, now let's go back. Let's change 2 of the 3 back to rates. What do you think will happen now? Suppose, well, okay, let's ask this. Let's keep it a timeout for getting infected, but let's make actually the recovery be a timeout, but then the loss of immunity be a rate. So we're only going to have a rate. We're going to have a rate purely for loss of immunity. Okay. You notice, by the way, it remembered the value when you changed it back to that. Okay. So in short, this guy stays a timeout. Infection. Recovery stays a timeout. And this one becomes a rate. What do you think will happen now, ladies and gentlemen? What do you think will happen as we run this?
Everyone will get infected at the same time.
Okay.
And stochastics in the recovery rate.
Okay, is it in recovery or in
The
waning of immunity? Okay, so no one's getting infected, they're all waiting their exact 365 days. And now suddenly, boom, they got infected. Okay, now what's happening though? Do you think the next round of this will all be occurring at the same time?
No.
What's going to happen now? Let's run it out. Now it looks like it's pretty well mixed here. People's cycles are off, right? They're off from each other. Even though now they have fixed times from lots of immunity to get to being infected, and from that to recovering, they're out of sync with each other. So it's pretty similar now, once they're well mixed, to the original situation. Let's go back and let's set it so that the rate transition, for example, it's a rate transition for infection, but everything else is timeout. What do you think will happen then? So only the infection one is a rate transition. Do you think I'll be able to tell the difference from the original one? It's pretty subtle. If it's there at all. It's only subtle statistics about how quickly people get recovered. Okay. Now I would ask you, is there any easy way within this model here, the stock and flow model, to make it so that people after exactly an amount of time go from S to I? How would I at least approach that? How would I make it so it's pretty close to exactly after a certain amount of time? Well, we could divide this up. People have been susceptible for 1 day, people have been susceptible for 2 days, for 3 days, for 4 days, and we could actually divide into many subcategories in a row. It would be very painful, though, to divide all these substocks up. And now I want you to ponder one more thing. And in fact, I'd like you to implement it, because all it will take is a minute. Suppose I wanted to keep track here, ladies and gentlemen, of the number of times a given person has been infected. How would I do that? Anyone? A variable. So we could go add in a variable here, count times infected. What sort of variable would it be? If it's a count, it would be a integer. Its initial value would be 0. And where would we increment it? At what point? When the immunity wanes? When the recovery occurs? Or when...
Entry to infected.
Okay, entry to infected. I like that a lot. So what we would do is count times infected. Now, for those with computer science background, you could do this plus plus. Otherwise, you could do this equals this plus 1 if you feel more comfortable with it. In any case, we could increment it. And by so doing, ladies and gentlemen, by running here, you could then go look at different people in the population. As we run this model, we could scroll down to a particular population member, and we could see this poor guy who's infected 601 times here. And they've been being infected over the course of time, pretty regularly. Okay, this poor chap with foodborne illness. Okay, so ladies and gentlemen, is there any way that you could easily keep track here of the number of times a person's been infected? How would you do that? How would you even think about figuring out what fraction of the population has never been infected yet? Have always just stayed here? Or how would you keep track of how many people have been infected 0 times, 1 time, 2 times, 3 times? What could you do? Well, you can make copies of this model. So basically, once people got infected once, instead of coming back to susceptible, they come back to susceptible after one infection, right? And then they get infected again and come back to susceptible after two infected. You can make copies of it. In short, you can organize the model by state, organize it by parameters, like we emphasized last time is the province of these models to do. You break things up by state, but it will be ungainly, it will be awkward. So for certain types of questions, it's much more convenient to simply add a variable, increment it, and we're done. Each person can keep track of their history, their particulars. Okay, so that's all we have time for today. Thank you very much for your patience. I'm going to ask you to review an additional video for Thursday, for meeting Thursday. Did I send that video out already? I know I said please watch this video. Did I give you a Thursday video already? No, okay. I'll send that along. I picked it out. I couldn't remember if I sent it. Okay. I'll be holding office hours as I am wont.